Yes, so good morning. We are going to do the project Synteny block detection using suffix tree algorithm. Basically, we are a group of three. So I will be explaining my part of this code and how this works. So basically, the starting is the abstract. So what we does, so we use as we have said, the topic is Synteny block detection involving conserved regions of DNA. So it is specifically we are using it by coding the sequence into blocks and studying the sequence alignment, and we bring out graph based techniques which can be used for large genome sequencing. So we use in this project we are using the concept of suffix trees. So and main important, and we use suffix tree because it is a powerful data handling technique and which effectively handles strings. So that's what we are using that. And secondly, the algorithm which I am using is Mckitren's algorithm. It is same to build suffix trees in linear time. So this basically allows us to have a more it's comparatively good algorithm. Basically there are other good algorithms, but this can also be used. So what's the advantage by using this algorithm is it's a speed, and it can be used to rapidly find the repeating patterns and gene orders without consuming a much amount of time, and it can be used for a larger genomic data set. So this is a effective algorithm in looking at the way it studied the genome sequence and conservation and evolution. So we are going with this algorithm because of the following reasons. Content of this PPT is the introduction, the objective and background, methods, current status, summary, and the references we have all used. References is not the references which I took in particular. It is as a whole the group which all references is been taken. So let's go. So let's introduce this concept of Synteny to you. So Synteny basically means the conserved order of genes or genomic markers across the chromosomes of different species. So what does it mean is like how two genomes can be evolved over time, or how can chromosomes be rearranged even if it is a function of certain genes based on their context. How can they be rearranged to form newer genomes? And so we all know the genome sequencing has become faster and cheaper. The massive amount of the data has been provided from organisms. We get a lot of data, so that makes this traditional methods a little bit slow and heavy. So we have that's why we have I have said before, we use suffix trees here because of its space efficiency, compactness, and the time in which it provides the information. This approach of Synteny block is much faster and much scalable as compared to the previous traditional methods, and which we can, and by using this method we can get the output and the genomic sequence in a faster and more efficient manner. So this is the background of how we are using it, using the Synteny detection. So there has been multiple sequencing alignment methods that has been conservatively used. However, these methods have less the scaling and the scale of the extent of the genomic size is much less and complexity is much less. So we have used graph based approaches like MC-ScanX. So these all have addressed these challenges, but still we have working out the best. We have working out in the speed of how fast we can get the results on. So as you can see in this slide, these are some of the methods being the background of how this can be done, the suffix tree implementation. So these are the methods which are the approaches which we can be used in finding it. So these are the methods we used. So as we all know, any project, first step is data collection, which we have collected from public databases like NCBI, GenBank, and NSML. So the approach is basically, we told before, suffix trees, and we use McGrath's algorithm. So this algorithm is important because it builds a suffix tree in linear time, meaning like construction status is like we have to extend completed to up to 70 to 75% of this project. So this basically includes the construction of suffix trees using McGrath's algorithm, examining the shared substrings, and maintaining a like identifying the candidate synthetic blocks based on the order of the gene and orientation. So this is what we have done so far, and we are trying to complete it by this month. So the summary of what all I've explained is been briefed by me again. So this basically involves detecting Synteny blocks. So we used Synteny blocks, which are perfected concept DNA segments between two genome, and we use this by using a suffix tree based algorithm. So this we use this because of its speed and accuracy, because those are critical in finding out those conserved areas. And McGrath's algorithm is a major strength, and the tool remains fast and efficient. So the inputs of genomes is like we grab the information, and a single suffix tree is built from them. So using the suffix tree, the common substrings shared by both genomes are being will be found, will be taken, and we highlight what's perfect conserved genomes where there is no mismatches and gaps. So importantly, this tool is designed to for like we can use it for a wider range of genomes. Even it is smaller ones or larger ones, we can switch accordingly and implement a direct comparison methods, unlike the conservative methods. So I'm here to give a brief summary of the code which I have done. It's not complete, but still it uses let me explain. So this is a Python script which we use to detect Synteny blocks between two genomes. So the sequences are stored in two files, FASTA files. So it defines a suffix class, like it is which builds a list of suffixes of given sequence, not the real suffix tree, but to the given sequence of the suffix tree. The longest common suffix method is the method being used. It compares all suffix of two sequences. We use a brute force approach for string matching. So, and the load FASTA function is being used here. It reads a file, extracts the header, read the full DNA sequence, and checks for basic validity, which means it is present or not. And we are in the main function, we load the script under two genome files, checks the length, and if it is small, it directly compares with the suffix approach. Like, and the what we'll do is the suffix, the script, the prints a position of matching segments, and it saves to another text file. So this is basically done in a 12 base Synteny block. So it is effective for short sequences, but for long large sequences it is useful, but more optimized algorithms has to be implemented for those purposes.